Welcome back. Today's goal of this lecture, till long day after, today I will see what some example of sequence of function. First example, which had come CSIR net June 2025 exam. The question based on Archimedean property. The question is, for each n greater than equal to 1, fn sequence of function from closed interval 0, 1 to r such that fnx equal to nx for if x belongs to closed interval 0 to 1 over n, 2 minus nx if x belongs to 1 over n to 2 over n open interval, after 2 over n to closed 1, this value is 1. Then the statement is, which of the following statement is true? Option 1, fn for n greater than equal to 1 converges uniformly on closed interval 0, 1 to a continuous function. Option 2, fn converges pointwise on closed interval 0, 1 to a discontinuous function. Option 3, fn converges pointwise on closed interval 0, 1 to a continuous function. And option 4, fn does not converges pointwise on closed interval 0, 1. Here fnx is nx, then 2 minus nx. When x equal to 0, then fnx converges to 0, and when x equal to 1, x equal to 0, fnx converges to 0 because nx, and when x equal to 1, then also fnx converges to 0. Now the question on the interval 0, 1. By Archimedean property, we all of us know there exists a natural number m which is greater than 2. Consider this is m such that mx is greater than 2. Then that imply 0 less than 2 over m less than x. And for all n greater than m, 2 over n is less than 2 over m. For all n greater than m, 0 less than 2 over n less than 2 over m less than x less than 1, then for all x belongs to 0, 1 open interval 0, 1, fnx means f1x, f2x, f3x, fnx, so on. And after fnx, this is, since this is less than equal to less than 0 less greater than 1, sorry, this is greater than 0 less than 1, after fnx, this belongs to, x belongs to 2 over, when x belongs 2 over n, close interval 1. Each term of the sequence after fn x in this interval eventually converges to 0, because in this interval, in the interval x belongs to 2 over n close interval 1, fn x converges to 0. fn x converges to 0 when x belongs to 2 over n to 1. So, limit function fx equal to eventually fx equal to 0. That means fn x converges to fx equal to 0 pointwise. Now we have to check, is this converges, is uniform converges? For this, here I will use the Mn test. Mn equal to supremum of fn x minus fx when x belongs to close interval 0, 1. Fx equal to 0, then that means this value is supremum x belongs to close 0, 1 fn x. And here the graph is look like when x belongs to close 0, 1, then this is nx. After that, this value is 2 minus nx. And in this interval 2 over n to 1, close to 1, this value is eventually close to 0. This value is 0. Here 0, here 1 over n, here 2 over n, here 2 minus nx. This is decreasing because gnx equal to, if gnx equal to 2 minus nx, then gn prime x equal to minus n. So this is decreasing sequence. So here supremum value exists at the point 1 over n. This value is supremum x belongs to 0, 1, fn x is nx, and supremum since at the point 1 over n, so this value is n into 1 over n, this value is 1. That means since mn does not converges to 0, so fn x does not converges uniformly fx. I hope my all viewers have understood this question. That means fn x converges pointwise to a continuous function fx equal to 0. This is be the right option. Here fn x converges pointwise to a discontinuous function. This is wrong. Fn x converges uniformly. This is also wrong. Fn x does not converges pointwise. This is also wrong. Only option 3 is the right option. To find the uniform continuity, here I have used the Mn test. Another method is, we all of us know, if fn converges to f uniformly, then limit n tends to infinity, integration 0 to 1 fn x dx always is equal to 0 to 1 fx dx. But this is the necessary condition when fn converges to f uniformly. But if this is true, this integral is true, that does not imply fn converges to f uniformly. Limit n tends to infinity 0 to 1 fn x dx means limit n tends to infinity 0 to 1 over n square x dx plus 1 over n to 2 over n 2n minus n square x dx plus 2 over n to 1 0 dx, and this value is limit n tends to infinity n square x square by 2 0 to 1 over n plus 2nx minus n square x square by 2 over n to 1 over n, this is 0. Then this value is limit n tends to infinity n square 1 over 2n square plus 2n times 2n minus n square four over n square by 2 minus 2n times 1 over n plus n square into 2 by n square, and this value is just cancel this part. This value is 1 over 2 plus 2 minus 2 plus 1 over 2, and this value is limit n tends to infinity this value would be cancelled. 1 over 2 plus 1 over 2, this value is 1, and limit n tends to infinity fx dx equal to 0. So fn does not converges to f uniformly, since this limiting value is not same. Next example, next question, fn x equal to x to the power n log 1 plus square root of x over 2 be a sequence of function on 0 1 close interval 0 1. Option 1, fn x is pointwise convergent on 0 1. Option 2, fn x converges uniformly on the compact subset of closed 0 open 1 but not on closed 0 open 1. Option 3, fn converges uniformly on close 0 open 1 but not close interval 0 1. Option 4, fn x converges uniformly on the close interval 0 1. Notice here fn x equal to x to the power n log 1 plus square root of x over 2. fn 0 equal to obviously 0, and fn 1 equal to here 1 log 1 plus 1 2 over 2, this means log 1. This is equal to 1 times log 1, this value is equal to 0. And when x belongs to open interval 0 1, then fn x equal to, since x to the power n log 1 plus square root of x over 2 on the open interval 0 1, x to the power n tends to 0, and log 1 plus square root of x over 2 is bounded. Since this is bounded and this is tends to 0, therefore their product function fn x converges to 0 pointwise. Therefore, whole interval on closed interval 0 1, fn x converges to fx equal to 0 function. That means fn x is pointwise convergence on closed interval 0 1. This is be the right option. Now I will see is this pointwise convergence is uniform convergence? Since here the question about closed interval 0 1 on the compact set, because sequence of function is defined on the closed interval 0 1. So here I will apply Dini's theorem. In Dini's theorem, since fn sequence of function is continuous and fn converges to 0 pointwise, and fn plus 1 minus fn, this value is equal to x to the power n plus 1 log 1 plus square root of x over 2 minus x to the power n log 1 plus square root of x over 2. This value is equal to x to the power n times log 1 plus square root of x over 2 times x minus 1. And on the interval close 0 open 1, this value x minus 1, since this is the x minus 1, this part is less than 0. Therefore, the sequence of function fn is monotone decreasing sequence. Since the sequence is monotonic sequence on the closed interval 0 1 and each function fn is continuous, so and the domain closed defined fn defined on the closed interval 0 1. So, by Dini's theorem, we can tell fn x converges to fx uniformly on closed interval 0 1. That means this is be the right option. Option 2, fn x converges uniformly on the compact subset of close 0 open 1 but not on the closed interval 0 1 on the not close 0 open 1. This is not true because fn x is converges uniformly on closed interval 0 1. Here also not true because here given not. So option 1 and option 4 is a right option. Now I will use here another method to find uniform convergence. This is MN test. Another method I will use MN test. MN equal to supremum x belongs to closed 0 1 fn x minus 0, and when x belongs to open interval 0 1, then 1 plus square root of x over 2, this value is less than 1. So log 1 plus square root of x over 2, this value is negative, not positive. This value is negative. Let gx equal to minus x to the power n log 1 plus square root of x over 2. And notice at x equal to 0, fn 0 equal to 0, and at x equal to 1, fn 1 equal to 1. Since fn is continuous and vanishes at the end point, so its maximum value attained in open interval 0 1. But when n increases, then x to the power n close and close to 1. Therefore, Mn, which is equal to supremum x belongs to closed 0 1 x to the power n log 1 plus square root of x over 2, as n tends to infinity, this Mn tends to 0, because log term approaches to 0 as x tends to 1. When x tends to 1, then log term always approaches to 0. So as n tends to infinity, this Mn actually goes to 0. Since this Mn actually goes to 0, therefore the sequence of functions converges uniformly on fx equal to 0. This is another method, but Dini's method is shortcut method. If you apply the Dini's method, then you can easily tell this fnx converges uniformly on the closed interval 0 1. I hope my all viewers have understood clearly. Okay? Oh well.